things aren't as they were before. You best start bracing. Did you think you could keep us out? Shut the gates, forget us now. Tides are changing. Can you hear this sound? Can't stop us now. the time, 'cause I wanna freeze this moment. Make it mine, hold you close. Now my heart's wide open. When I'm with you, suddenly I feel no pain. Do you make it go away? Do you make it?
Good evening and welcome everybody. This is Obi-Wan Pezor Simplex Pachinko. We are going to be working on some math tonight. As per usual of the lately stream, whatever, of the stuff we've been doing lately. We're working on cracking the GRE, which is the Graduate Record Examination. And we're going to look at going through the next section, which is going to be on other conic sections. So we're currently talking about circles, ellipses, and no, sorry, we did circles and we did talk about parabolas. Hey Seth, hey Jeff. Yes, but which of us, Jeff? Ayo. Alright. All of humanity. Alright, cool. And Seth, what would you be interested in if we did such a thing? Gotta ask specifically, right?
Take me away from home.
I feel like this is small.
Show me all the places I've never known. It will chase.
I mean, these do lead up to individual questions, and then there is a large series of questions at the end. Just, you know, we haven't gotten to the trigonometry stuff yet. Yeah, Chapter 1 review questions as of page 26. This is still loud. I forgot. Hey. Yes, that's a good point. That is the GRE math test. So... I think this is night 3. I would love to be able to tell you, but unfortunately, my video archive has been acting up. Oh, in fact, all of Twitch has been acting up the entire day, but that's not the point. So, yes, that does also mostly work. I do typically find that that's kind of how I started my teaching career, was basically being given a lot of individual problems and then just like going from there. I found that at the very beginning of looking at material, did not particularly understand it. I was just going through and being like, here's how to do the thing. And so going through the actual chapter section that it's talking about does, at the very least, like make the individual connections with stuff I've already taught, stuff that, you know, other methods that I know, and it seems to at least help in some way, shape, or form connect those up in my mind. Now, I don't know how anybody else feels about it, apart from, obviously, Seth. But... Oh, that's gross. All right, so yeah, I'm just finding it difficult at this point. If I don't talk about this stuff ahead of time, then it's going to be like, here's a question, and then we're just going to have to look up the answer again either way. So, like, it's going to burn off the same amount of time either way, pretty much. How many topics are left? Well, I mean, we've got all of trigonometry still. Logarithms. Polynomial equations, which include division, remainder, and factor theorem. Fundamental theorem of algebra, roots of polynomials. And arcs. Ellipses and hyperbolas. Yeah. Right. Let's turn the fan on. Sure, we can try it. Alright, when you're looking at an ellipse, there are two ways that it can mainly go. We said that before we didn't really want to have the xy term, the mixed term in there, all that often, at least, you know, at the beginning anyway. So b, the coefficient of that term, is going to be equal to 0 for the most part. Having that term is going to have this kind of rotated into an off direction where these are not going to be aligned with the axes. I mean, day's going pretty well. It's alright, thanks. How's everybody else? How are you all doing? Kids got into a fight this morning, so that was fun trying to referee that. And then they just went to school, so they didn't see each other for 6 hours, but then they came back and they... Yeah. Okay. So most of the time we have something that looks like x squared over a squared plus y squared over b squared is equal to 1. In this case, we have this centered at 0, 0. A, in this particular case, is going to be the semi-major axis length if, and this is kind of an asterisk here, if this one's longer. So, without loss of generality, right, the longer one is going to end up being the semi-major axis length, and the smaller one is going to be the semi-minor axis length. On our diagram, that's going to be this one right here for A, and this one right here for B. Interesting. Okay, maybe that's not a misprint. Interesting. That can't be right. Yeah, okay. Longer axis of symmetry of the ellipse is called the major axis, and the shorter one is the minor axis. In the next two sections, where it lists like how to find them, here's your quick reference guide. It says the manner axis length. Oh no, they got that misprinted too. Lengh for length, and manner instead of major. But hey, you got to put some misprints in, right? So you can sell a new copy later. Ayo. No, most people don't do that. Okay. We also have the vertices, which are going to be located at the ends of the major axis. Which in this case is plus or minus a comma 0. Oh, no you don't. You go to sleep. Come on. This computer's been acting up all day. I mean, so is Twitch, but nonetheless. All right. I'm going to need to move some of this stuff around on my desk because this is getting untenable. There's just too much stuff up here. Okay, and then we have our we have our foci, so this is going to be 2 focus points. So unlike the parabola, which only had 1 focus point, our ellipses, right, and our circle technically has a focus point. It's called the center. The focus points on an ellipse are not going to be any of the previous points that we've seen. Right? It's going to be something similar to a parabola, but again, this is going to be of like a finite distance on our cone that we were looking at. So now we're going to have 2 individual focus points. Now the awesome fun fact of the day here is that our focus points for ellipses will end up causing every single point on the ellipse to be defined such that let's call this F1 and F2 going out to any particular point xy have the special property that F1 plus F2 is going to be equal to some constant. So we'll just call it K for now. So it's really cool. You can always just move that around anywhere you want on the entire ellipse. This is actually how I build an ellipse in my pre-calc classes. So you tack 2 strings to the board, or a string in 2 places that has a little bit of give to it, and then you put it out to its maximum length, and then you just trace it until it goes all the way around pins, and then you got to swing it back underneath and go the other way, etc. And you end up getting a nice perfect ellipse. You know, subject to errors, the standard errors when you're just drawing things, because you're going to make errors. Naturally, when excuse me, when we're all the way out at either of the vertices, we're going to end up with like F1 is equal to the vertex to focus length. Kind of curious if that has a special name. And then F2 is going to go from the other focus to that vertex as well. So the sum of the two distances to that vertex from each of the foci. Right, without actually putting any specific numbers in, that's going to make it a little bit more difficult, but why do ellipses appear like that from any two focus points? So it's probably a good question, and I should probably be able to come up with a good answer. On the spot. So I think what's going to essentially happen here is that if we were to break this down and say, hey, let's do some like looking back to trigonometry and all that good stuff. One of the things that we could do is say like, okay, well, we know that for this particular point, this is going to be x, right, going out to here. And then we've got the distance from 0 to focus 2, which I guess we could use capital letters for this. And then here, this is going to be focus 1 with capital letters again. So then we could come up with a relationship that exists between these particular values, both a and also x and our capital F's and our lowercase f's. So we've got Pythagorean theorem going on in a couple of places. And again, no matter where you go in the plane, if your foci lengths are always going to be stretched out, then you end up with like the same relationship everywhere you go. And we should, in theory, we should be able to come up with the equation of the ellipse from this picture. Now, I'm not seeing it right offhand, but right, capital F1, capital F2 always stay the same. Yep. And in fact are the same distance. So we could just let that be capital F. Right. Has to be the same distance. Now, that is from the center. So the center itself could have been shifted around all over the place, but it's not really the point. Yeah. Area and circumference. So that's going to be a bit harder, but... Alright, so we got the equation up here. So it looks a bit like the equation for a circle, but then you have differing numbers in the denominators on the left-hand side. In theory, right, for circle, we could have done either x squared plus y squared equals r squared, or we could have brought the r down and made it x squared over r squared plus y squared over r squared is equal to 1. Note that in the case of the circle, right, the r squareds on each of these things is identical. So that is your semi-major and semi-minor axis length. It's r. It's the radius. Of course it is. But then you start getting into ellipses, and now those distances are going to be different. Because the ellipse is now like a circle, but now it's been stretched in one or the other dimension. Yeah. Yep. Yes, yeah. if A and B are the same number, then that is the radius, and it is a circle. So let's see. Yeah, I've never actually proven it from standard focal length like that. Oh, this is Y, right? So again, it should be sort of easy in theory. We could also do the extreme case where we just look at the one where it's at the top of our semi-minor axis, and then also at the end of our semi-major axis. And if we do those extreme cases, then like our x and our y respectively will be 0. So then we just have to like figure out what the other bits are going to be, but feel like that might be oversimplifying. I don't know. We'll see. Yeah. Now, circumference and area I can only do using calculus because it's been such a long time. In theory, I could, run through the book and try to find what the formula is, but or just look it up. But we could do it using calculus because it's not too bad. Yeah. No, those are both Calc 2. Well, you could do Calc 1 using yeah. We could do area for Calc 1. We can do Calc 1 for area. So if we let this be a particular, right, x squared over 4 plus y squared over 9 equals 1. Okay, this is actually an ellipse that goes this way, but whatever, it's fine, right? That's also terrible because it's not distorted that much. It's more like that. So choosing perfect squares just makes it easier to work with because now I can say that, okay, well, this has a semi-minor axis of 2 and a semi-major axis of 3 in those respective directions. But again, it doesn't actually matter. We could do it in general using the A and B as well. It's just going to take a little longer. No, it's going to require Calc 2, but it's not that bad. So we do need a what's called trig substitution. It's a little bit like U sub, but instead you use specifically trigonometric functions in order to defeat the square root function. Defeat. And in this particular case, if we want the area, we can actually say, look, we're going to take the area of the thing that's just going from 0 to 2 in the x direction. So we're going to go from 0 to 2, and we're specifically looking at this curve here. Right? And then we're just going to say, well, that's the same as that, and that, and that. So we need something that's going to be 4 times bigger than just the 1/4. Right, use symmetry to your advantage. You don't have to do all of the, complicated stuff. So we're going to go from x equals 0 to 2 and have just the top quadrant, stuff in the first quadrant we're going to do the integral in order to get the area, and then for the rest of it, we just say multiply by 4. Again, make it easier. So that means we need to solve for y and make it just what's the function in the first quadrant. So for this one, we're going to get a 1 minus x squared over 4, multiply by 9, and take the square root of all of it. We're just looking for the stuff in the first quadrant. True, area formula would be a goal. Alright, so if we do that, then, oops, no, we're good, we're good. We don't need the b in there, right? The b could be taken out entirely. So we can make this y equals square root of, the 9 could be factored out, make it 1 minus x squared on 4. And in fact, we could factor out the 1/4 as well. Turn this into 4 minus x squared. This will make it easier in the long run to deal with. So then y is equal to 3/2 of that square root, 4 minus x squared. How we doing? Yeah, still on the page. And it doesn't look like it, right? So at the moment, it seems like, how can you possibly even think about getting that number? Anyway, we'll get 3/2 square root 4 minus x squared and dx. So from here, we don't have a u substitution because the derivative of the inside would have to be negative 2x. So we just don't have it. Alternatively, we could look at this and say, hey, that looks kind of familiar. This is the hypotenuse squared minus a leg squared of a right triangle. So if we were to build a right triangle like this, we could get that the length along the hypotenuse is 2. Again, 2 squared gets you the 4. And then 4 minus x squared. X would be one of the two legs, doesn't matter. And this would all get you this leg here. This is going to be the square root of 4 minus x squared. Yeah, the 3/2 can go out entirely. Which you'll notice is also b over a. Yeah, in this particular case. We'll come back to that. Okay, now I don't really need this all that much, but I'm just going to leave it there because it's the length of the third side of this particular right triangle. So essentially what we're doing is we're calculating, like, what is that, what is the height of that particular point at anywhere that we go along that curve. Okay, from here, what we do is we say, well, there's a relationship that exists between theta and x that's super easy, right? This is that the sine of theta is equal to x over 2, or x is equal to 2 sine theta. Depends on which way you want to bend it. It doesn't really matter to me. I don't really care. Dx is equal to, this would be 2 cosine theta d theta. Okay, and then using these two things, we want to then replace all of this stuff that has x's with all of that stuff down there which has thetas. So the area is going to be equal to, this is going to be 4 times 3/2. Integral. Now here's the thing, right? This is x equals 0 to 2. This is theta equals, right? If theta were, if x were 0, then how do we get a sine function to end up being 0? Well, that's at 0. So that's easy enough. We got a starting point. What about the end point? Well, we want the x value to be 2. So the x value is going to be 2 when 2 sine theta is the other side. So how do we get theta there? That's going to be 2 times 1. When is sine of theta 1? It's at pi over 2. Or 90 degrees if you prefer. Heathens. Okay, so then we go in and we say we're going to get the same square root function, and it's going to be 4 minus parentheses. Here x squared is going to be 2 sine theta squared. And that multiplied by dx, which is 2 cosine theta d theta. So now we look at this and we say that area is going to be equal to, here we get 4 times 3/2. Yes, I am leaving it unmultiplied for a reason, right? Let's see where the pattern goes. Theta goes from 0 to pi over 2. This is going to be the square root of 4 minus 4 sine squared theta times 2 cosine theta d theta. Okay, what's all this stuff? Hey, what do you know? This is going to be 4 times 1 minus sine squared theta, which is going to be 4 times cosine squared theta, which, when we take the square root of all that, yep, becomes 2 cosine theta. And since we are in the first quadrant, we don't need to worry about pluses and minuses or absolute values or any of that. This is also why I suggested not bothering to use the second quadrant or the third or fourth, right? Just use the stuff in the first quadrant and utilize symmetry, because now we don't have to worry about, again, pluses and minuses and all that other stuff. If you did, it's still going to work itself out, so you don't have to worry about it too much. All right, this is times 2 cosine theta d theta. Still 4 times 3/2. And then this is where it gets a little more interesting. So if the area is that, watch out, the floor is lava. This is the integral as theta goes from 0 to pi over 2 of 4 cosine squared theta d theta. Again, you could pull out the 4, that's fine. And it's the integral of cosine squared d theta. So, it would appear that we get stuck yet again. However, anybody who knows their trig well enough knows that we have a power reduction formula. Yep. Power reduction formula comes from, if you remember, the cosine of 2 theta is equal to 2 cosine squared theta minus 1. So, rearrange. And we end up getting that the cosine squared of theta is equal to, leave that where it is, add 1 to the other side, so we get 1 plus cosine of 2 theta, and then divide it all by 2. Because now, what we have is 1/2 plus cosine of 2 theta over 2 all d theta. Yeah, but it's not that bad. See, here's the thing, right? When you take the integral of cosine squared, you're kind of stuck from all of the old methods that we learned, right? You're stuck from using, there's no u sub. Here you've got, if you said, well, if it's a u is the cosine of theta, then du would have to be the sine of theta, or negative sine of theta, and we don't see that anywhere. So if you have both sine and cosine, you're in luck, because now you can be able to get something that has, yep, you will be able to get something that has a sine and a cosine. One of them is to a higher power, and then therefore that one ends up being, you know, your u. And then the one that's a single is going to be our du. But here, right, we don't have that. We don't have anything. So instead, we use this power reduction. Which again, comes from the double angle formula. We just rearrange it. It makes this power reduction formula. Now, cosine squared of theta becomes 1 plus cosine 2 theta all over 2. Well, now it's just a single cosine. So we don't have to have another sine or cosine or anything else attached to it. It's just here. We could just say, well, if this is going to be the integral of, right, integral of a half is super easy. That's just 1/2 theta. Plus, then here, the integral of a cosine is going to be a negative sine of 2 theta, the same thing you had in the first place. Then what we have to have is, right, there was a 2 there beforehand, then we have to have du. Well, this was u, so du is going to be equal to 2 d theta. We don't actually have a 2 here, we have a half. So what we can do is say, let's multiply by 2 over 2. That 2 is going to now become part of d theta. And then this 2 here becomes part of our denominator here. Right, and then all of this is taken from, again, 0 to pi over 2. Yeah, now it's u sub. I mean, yes, we could always get Zach in here to fix it. Right, so now we get pi over 2, half of pi over 2, minus 0, so that's gone. And then over here with sine, we end up with a minus sine of 2 theta is going to be sine of pi. So that's 0. Or sorry, sine of 2 times pi over 2 is going to be the sine of pi, which is 0. And then we get minus a negative is plus. The sine of 0 again is 0. So now we just get pi over 4 multiplied by, in case you thought I forgot it, all of this stuff that was out front. So now this is going to be, again, this is going to be 4 times 4 is 16, divided by 2 is 8, times 3 is 24. Six pi. Yep. Yep. So, right, if we quickly do it in general, whoop, if we quickly do it in general, then we're saying that we want, again, this thing needs to be y equals. We shift everything around. This is going to be 1 minus x squared over a squared. We're multiplying by b squared everywhere, and then taking the square root of all of it. Again, just worry about the first quadrant, and then multiply by 4. So y is going to be equal to, this was b times the square root of 1 minus, b over a, and then this will be a minus x squared. Right, this is the same path we took with the other one. Just keep it the same path so we don't get confused. So then the area is going to be equal to the integral, 4 times the integral, of b over a times square root a minus x squared dx. And then we go the same route. So x is going to be equal to, same deal as over there, that's going to be a. That's an a squared, sorry. Inside the square root, it's an a squared. Right, a sine theta. So dx is going to be a cosine theta d theta. Right, so area is going to be equal to 4 times b over a times the integral. This is where x goes from 0 to a, right? The end of its axis. And then that's going to make theta goes from 0 to pi over 2 still. So no matter what a is, theta is still going to go from 0 to pi over 2. And you could double check that with these values here to make sure that I'm not lying about that. Yep. And then we get the square root of a squared minus x is equal to a sine theta. So this is a squared sine squared theta. And outside is a cosine theta d theta. Is equal to 4b over a integral 0 to pi over 2 square root of, here the a squared can come out and make a on the outside. That's pretty nice. So here our a's go away. This a can come out. So now we've already got 4ab just stuck on the outside. And then this is going to make 1 minus a squared times 1 minus sine squared theta, which again is a squared times cosine squared theta. The a squared comes out to make a. We're just left with cosine squared theta on the inside with a cosine theta d theta out here. And now it all turns out to be just the same stuff. Yep. So 4ab times the integral of, this is going to be just cosine squared theta d theta. We already did this. Again, this is going to be 1/2 plus cosine of 2 theta over 2 d theta. This is going to be a 1/2 theta plus is going to be, no, minus a 1/4 sine of 2 theta evaluated from 0 to pi over 2. Again, this is going to be pi over 4 minus 0 plus 0 for sine. And then again, all of that times 4ab. So, AB pi. Yeah, circumference is going to be a bit tricky. Um, hmm. Fair enough. Yeah, typically the way that we look at arc length is we say if we want to figure out like a small piece of this, say from here to here, then what we do is we pretend that it's linear, just for a minute. And then we say, how do we get a linear distance? Well, this is going to be a delta x and a delta y in a right triangle. And so the way that this gets set up, right, this is going to be our delta d, d1, di, whatever you want to call it. It doesn't really matter what it is. So, right, delta x1, delta y1, or I. For all d sub I, this is going to be equal to the square root of delta xi squared plus delta y sub I squared. Right, now this is a calc thing, but whatever, it's fine. So what we can do is look at this and say, you know what? This looks sort of familiar to me from Calc 1. What we can do is pull this part out. D sub I is going to be equal to, if we factor out a delta x sub I squared, again it gets square rooted and becomes a delta x sub I multiplied by the square root of 1 plus delta y sub I over delta x sub I parentheses squared. Also, that looks familiar. What is a delta y over delta x? Well, from all of our calculus stuff, if we shrink this down to basically nothing, this becomes dy dx parentheses squared. And this delta x ends up sticking on the end as a dx. That's equal to a particular infinitesimal distance. Well, then we sum all of them up, right? So if we sum all of them up as the limit of I goes to infinity, that's a bad idea, sorry. I goes from 1 to n, where n goes to infinity. Then this ends up with the true distance is equal to the integral from A to B, right, particular area. Seth, which part? Sorry, I missed when you said y. Or if I have resolved that since then that's fine. Dy over dx is just f prime, right? It's your function derivative squared dx. After you stated the research. So it's going to cause us to require those particular things because when we right, so when we take the y formula that we had up to, in fact, we don't even need that. Let's do the derivative from the equation itself. So taking the derivative of x squared over a is going to be 2x over a squared, plus, let's redo that, 2x dx over a squared, plus 2y dy over b squared is equal to the derivative of 1 is 0. I want to get dy alone on this side. In fact, I want dy dx, right? Dy dx is equal to, the dx part is going to shift over to the other side. We get 2x over a squared. This is still multiplied by 2y over b squared, and then we're going to multiply that through as a reciprocal. So dy dx is equal to, our 2's divide out. All right, we could do that here. We could do it somewhere else. It's fine. We end up with b squared up top with x and a squared on the bottom with y. So that y, if you remember from earlier, squared x over a squared times the square root of, that was that. B over a times square root. All right. B over a times the square root of a squared minus x squared. Okay, now we need to feed it into here. So our distance is equal to, this was a terrible idea. So the distance from A to B, great idea. Again, we can just do like a quarter of it. Again, this is going to be from x equals 0 to 2. We're just going to do the 1/4 and then multiply it by 4. This would be the square root of, adds are going to start in a minute 15. I'll take a quick break. Dy dx squared. The b here gets rid of the square there. The a here gets rid of the square there. Then, doing this thing, doing this square is going to reinstate all of it. So this is going to be b squared x squared over a squared times a squared minus x squared dx. Right. So, like, trying to find a closed form of this thing is virtually impossible. We don't have any way to do a u substitution. There's no nice way to make it work. So we just kind of like backed ourselves into a corner by doing this. There are some ways to do it. However, you would need to either, you can use approximations, or if you know complex analysis. So that's like Penn Center's big one. You can actually use complex analysis to solve a lot of these impossible integrals. Break time. Perfect timing. Uh-oh. So last time we didn't actually talk about the hyperbola equations. We talked about just like that they exist. Always lift with your back. No, wait, that's wrong. Dost thou in hoist? So the area from the focus isn't actually too bad. Mostly because the we could basically just take the equation and shift it, right? So we take any we take the equation of a regular ellipse and we just shift it to the left or right to put the focus on 0, 0. And then when we do that, our horizontal direction will just be off by a plus or minus c, whichever direction we feel like shifting it. Then we would take a yeah, that. But we take an integral that starts from the focus, and then it's a wedge slice. Right, so the question that is like the next example in the book. So sum of distances from any point on the ellipse xy to the foci located at plus or minus 2, 0 for a particular ellipse, right? This is not going to be necessarily nice. Is equal to 8. Right, find the positive x such that x, 3 is on the ellipse. Okay, so without looking at the answer, So there's a few assumptions that are being made, right? That you just have to kind of register in your mind that yes, this is going to work for us. One is that our foci are located at plus or minus 2 comma 0, which means that they are symmetrically positioned about the origin. So we have our axes like this. We know that plus 2 and minus 2 comma 0 are going to be the foci, which means that 0, 0 is the center. So it's not like it's actually necessary to the problem, because we just needed to find, you know, the location x comma 3 that's on the ellipse. But it's important to recognize just in your mind that, yes, right, this is now causing us to have the center at 0, 0. Right, if this is located at 2 comma 0 and this is located at negative 2 comma 0, right, we could kind of go back on what we were talking about before, where like if we go like this, we will know for a fact that we could create an isosceles triangle along the y-axis such that we end up with our, right, the sum of distances from any point on the ellipse xy, so let this be on the ellipse, located, or that goes to each of the foci at plus or minus 2 comma 0 is going to be 8. Therefore, these are going to be the same, and so therefore they're going to be 4 each. So we could actually figure out what the semi-minor axis is going to be pretty much immediately. Now that I say that, it might not be the semi-minor. This might be the semi-major. No, that's semi-minor. Right, because the foci are always going to be in the direction of the semi-major axis. Right. Yeah, we could move the foci around using transformation and end up with, at the very least, putting them on a predefined line. We would normally just have them shifted orthogonally, so they're just going to be moved around like this, and so they're not going to end up being tilted. Again, our b value from that long equation is going to be 0 most of the time. Yeah, oh, that's fine. So even if it's up here somewhere, you just say, here's the origin, let's recenter. Right, because we know how far apart they are, as long as you have their coordinates, right? Yeah. Yep. So if they were at negative 2, 0 and 1, 0, then we can just shift a half to the right, right? And then it would be at negative 1.5 and positive 1.5, comma 0. So it makes it real easy to work with. Right, the other one here, if we go along the semi-major axis, this is going to go out to like here, and then this is also going to go out to here. Right, so the sum of their two needs to be 8. What's going to happen here is that we have a distance of 4 is already taken up by that distance going across, and that's kind of nice. Okay, so that actually makes an equilateral triangle. That is not always the case. Right. And so here we'd say, well, I don't know what this is or this is, but knowing that 2x plus 4 has to be equal to 8 is pretty helpful. Right, so x equals 2 here. We don't really have to think about it all that much, but it also makes sense when you say this, right? This is going to be 6, and then that's going to be another 2. So, we got it. Right, so this ends up getting us our semi-major axis, which again shows us that it also goes in the other direction the same amount. So this is going to be a negative 4, 0. This is going to be 4, 0. This, we already know what it's going to be, right? This is 2. This is 4. So this is going to be 2 root 3. So in this particular case, it worked out very nicely. But if the foci were located at plus or minus 3 and the sum was still equal to 8, that would be different, right? That would make a different ellipse. No, the foci aren't touching the ellipse. The foci are at plus or minus 2, 0. The endpoints of our major axis are at plus or minus 4, 0. Yeah. The distance between the foci was 4, but that's not the distance on each side of 0. Right, so we had 16 minus 4 got us 12, which gets us 2 root 3 as the square root of that. Yeah, okay. Hello, Meowweather. How are things? Welcome back. Now we're hanging in there. Working on this GRE stuff, which is leading us into some, back channels of some information there. However, Sunil would approve, right? We don't always need to run through and discover all sorts of, we don't have to necessarily always be on task for the goal. Some of these things that we're discovering here are just nice little back alleys and back channels to get the kind of information. Yep, we're looking at the GRE math test. And currently looking at the Conic Sections part of Precalculus, which a lot of people don't use. Yeah. See? Yep, so we were just looking at ellipses and we were trying to find like what's the area and what's the circumference of an ellipse. So the area ends up being fairly easy to work with. We just did 1/4 of it and then multiply by 4 because 4 quadrants. It does take some Calc 2 to actually prove it, but the amount that we got, right, the formula that we ended up getting was AB times pi, where A and B are the semi-major and semi-minor axis. So pi times the product of those two axes. Jeff, were you thinking it was Merriweather? Yeah. Nope, just different person. So we end up with something that looks like this. I say like this pretty loosely. Okay, and we want x comma 3 to be on the ellipse itself. 2 root 3 is a pretty close value to 3 itself. So 3 square root times 2 is going to be 3.46. So we want to know where this point is right there. Okay, so let's, before we attempt this, let's build another one down here that looks better. Right, or at least it's clean from all of the other gross stuff that we put on here. So we said this is going to be -2, +2. This is 2 root 3, so it's 3 something. This is 4 and -4. Okay, and then whatever, it's here. So make the point big enough no one will ever know. Okay, so this is going to be our x comma 3. We do know that the distance that goes from each of the foci to that point has to sum up to 8. So f1, f2. We also know that that distance here, this is going to be 3, and this is going to be x. We also know that this distance here was 2, and this distance here is 4. Woohoo! Alright, this distance here is 2. That should be all we really need here. So f1 plus f2 is equal to 8. Okay? Now we work out a formula to find what are the constituent parts f1 and f2, or what are the constituent parts of f1 and f2. So f1 could be the hypotenuse of this triangle here. It's a right triangle, unlike the one I just drew. So we do know at least that f1 squared is going to be equal to parentheses 2 plus x squared plus 3 squared. Right, so f1 is going to be equal to the square root of This is going to be, I guess we could just leave it as is. 2 plus x squared plus 9, or 3 squared if you prefer. And then f2, right, builds this right triangle. So f2 squared is going to be equivalent to parentheses 2 minus x squared. Yeah, the positive x only. So we don't want the one over there. We just want the one on this side. Okay, so, and again, we just want the one up top because y was 3, so we didn't have to worry about that. Plus, again, 3 squared. So yeah, f2 is equal to the square root of 2 minus x squared plus 9, same deal. So the sum of those two things has to be equal to 8. Now, we did this in my pre-cal class, not with this stuff. Right? We actually looked at this in isolation, and I cursed it every... Oops, I flipped the squared in parenthesis. Okay. We looked at examples that were the square root of something plus the square root of something is equal to a constant. And then had to solve for one of the terms, or, you know, find where x is in this whole thing. Oh, doesn't it? So here's the thing. It is not quite as simple as we want it to be. Yeah, the issue is that this has a square root plus a square root. So when you square the whole thing, you get two individual square roots, which go away. But then you have the cross term, which everyone forgets, which is going to be the product of the two square roots. So what I prefer is to go the other way. Not that it matters, but go the other way and say, okay, what we really care about here is that we're going to end up with an x value which we know should be between 0 and 2. Right, it's going to be on the other side of the focus. Do I know that for absolutely certain? Maybe not, but I'm pretty sure we can figure that out from here, where this is 2 minus x. Right, so if we end up with... I mean, it is the restriction, right? It's just that one part of it. And then technically, like, even if it were negative, we square it so it becomes positive again. Like, oh well. It takes care of the idea that, like, if we had x over here, right, then the distances that we're dealing with are still going to be x to get out to that point, and x, or 2 minus x. I guess technically it would be x minus 2 would be the other distance. I mean, you shouldn't have a negative. Oh, yeah. So the inside has to be greater than 0, or greater than or equal to 0. But if the inside is greater than or equal to 0, it's the sum of two squares. So two numbers that you have squared are always going to be positive. So sum them up, you're always going to get a positive. So yeah, none of that. We just, yeah, okay. So I guess technically we don't know that it has to be less than 2. It definitely has to be less than 4. Because otherwise that puts it outside the ellipse, and that's bad. But realistically, I want to say that that's going to be less than 2 as well. We'll see. Okay. Sure. Keep the 1 over here. That's already positive. I know, it doesn't matter. And then over here, 2 minus x squared plus 9. Right? Square both sides. Square both sides. So now we get the sum of 2 plus x squared plus 9. Okay. And on the other side we get 64 minus 16 times the square root plus the stuff that was inside the square root. 2 minus x parentheses squared plus 9. 2 minus x squared plus 9. Alright, now shift everything to the other side. Hooray! Yeah, I would say multiply these out. So 4 plus 4x plus x squared plus 9 is going to be equal to, here, 64. We get minus 16 times the square root of that stuff. And then here, this is going to be 4 minus 4x plus x squared plus 9. Okay, so here we got a 9 on both sides. Get rid of it. We've got a 4 on both sides. We've got an x squared on both sides. Get rid of all that stuff. Now we just have to move the negative 4x and the 64. Cleans it up a bit. So this is going to be 4x plus 4x is going to be 8x minus 64 is equal to a negative 16 square roots of parentheses 2 minus x squared plus 9. Okay, we can divide by a negative 8. Negative x plus 8 is equal to a positive 2 square root of, not that any of this matters, right? It's all going to end up coming out a bit nicer in the end, because we still have to square everything. Square everything again. All right, up here, this was all of this stuff squared. So you do have to watch out for your cross terms and all that good stuff. Okay, this is going to be x squared minus 16x plus 64 is equal to 4 parentheses 2 minus x parentheses squared plus 9. Right, this is now going to be x squared minus 16x plus 64 is equal to 4 times, this is now 4 minus 4x plus x squared plus 9. This is going to be, let's see, 4 plus 9 is 13 times 4 is 52, minus 4x plus x squared. We now no longer have an x squared on both sides. That's all we can say for that. Okay, minus 16x plus 64. Move the 16x that way and move the 52 that way. So this is going to get us a 12x on that side, and this is going to get us an 8. 12. 12. X equals 1. Woo! Oh, no, you're right. Boo. Boo, Obi boo. I forgot the 4. You're completely right. Yep. No. Not you. Right, this is a 16. This is a negative 16x. This is a 4x squared. This is a 36. X squared minus 16x plus 64. Okay, try that again. So, since this is now an actual quadratic, shift everything that way. So 0 is equal to, yes, you got 3x squared. A negative 16 plus a 16 goes away. And now it's a quadratic without a middle term, so we can move all the rest of the crap the other way. All right. Still 12. Okay, so let's see. We multiply this out. That's going to be 4 minus 4x plus x squared plus 9. Multiply in the 4. Gets us a 16, a minus 16x plus 4x squared plus 36. 36 and 16 is 52. 52 from 64 is 12. So we got the left side. The right, minus x squared here, minus 52 here, plus 16x makes that go away, minus x squared gets us the 3x squared, and then, yeah, minus 52 on both sides gets us the 12 left over. Okay, so x squared is equal to 4, which means that the absolute value of x is equal to 2, which in our case means we just want the positive 2 in the first place. So this ends up creating a right triangle directly over our positive focus. All right, you said you had... Thank you very much for the follow. You said that you had a 4 minus 1/2 x all squared. 4 minus... Okay, so you've got both a 4... Yeah, your 4 is too high then, and your 1/2 is too low. It's like you took... it's like you did that slip, slide, divide thing. You divided by 16. Okay. So when you divide it by 16, then it should have gotten you a 1/2 x minus 4. when you square it, I mean, it depends. So I just divided by positive 16. But, I mean, if you divide it by negative 16, then that's fine. It doesn't matter. Either way you go. But sure, let's make it a... Yeah, negative. Alright, negative 16 makes that a negative and that a positive. Okay, so then that would have been divided by negative 16. You're just left with the square root of 2 minus x parentheses squared plus 9. All of that is being squared to get on the left positive 1/4 x squared. Okay, the negative is going to multiply the positive. We end up with 2x, but it's going to be negative 2x from two different directions. So that's going to be a negative 4x. I think you already had that, yeah? Yeah, you had the negative 4x. Okay, but then this is going to get us a 16 on the left. Okay, you missed your middle term. Yep, I see it. Right, this is one of those things that you really have to watch out for. Not just that. Oh, and twice as many. Yeah. Minus 4x plus x squared plus 9. Right. So if you just went from here, that's going to be minus a quarter. Yeah, we do get the negative 4x on both sides, which that can make that all go away. And then 16 minus 9. Oh, right. The 4 is there as well. So add that. That's 13. That's 13. Right. Bring it over. This is going to be 3 is equal to, this is going to be 3/4 x squared. Okay. So now x squared is 4. Good. Yep. As long as we end up getting the same thing, right? Yeah, I just try to avoid fractions mostly. It's maybe an awful thing for me to say, but nonetheless. All right. Hey, Zach, how's it going? So Kepler again, if we use the focus as the origin point, and then try to say like, all right, we need to sweep out the same area. What is it actually? I know it's the same amount of time when you parameterize it. But it's also the same angle? Is that it? Yeah, it's the same time. Yeah, it's not the same angle. Okay. I was hoping. Because, like, the same angle out here ends up making a huge change compared to same angle in here. So yeah, that's not going to work. But yeah. Fair enough. Yeah, we're going to need laws of motion for that one to figure out what the same time is going to be. A cosine t, B sine t. Well, yeah, but then I've got to shift it. So that's going to be, what, x? Is it really just that easy? X plus 2 or whatever? That's also technically the simplified version because three-body problem and all that. Yep. Planets aren't point masses. No, but they're really close, comparatively. When you consider the distances that they're going, like, away from each other, right? Even the Earth and the Moon are, like, 250,000 miles apart, and, you know, the Earth's radius is only 4,000, I don't know. 6,300 kilometers, which is roughly 4,000 miles. Yeah. So you think about it, right? It's still. I guess. Yeah, no, yeah. If you look at Sun, Earth, Moon, or Sun, Earth, Moon, Jupiter, right? So you get 4 bodies in there. Like, even that starts throwing stuff off because now the paths aren't purely elliptical, and even if it didn't involve the moon, Sun, Earth, Jupiter, or Sun, Earth, Jupiter, Mars, you start getting a lot of deviation from perfect ellipses. But, like, it's pretty close. I mean, that's the good question, Seth, is, let's try flashbang. Thanks. Okay, from 1 to 10. Cool. Okay, so going from t 0 to 2 pi, we end up getting one ellipse, one complete ellipse. And then I said, what if this was like 2 plus that? Yes. Okay. So we just need to look at... Right, so if we end up shifting this over... Hang on. That was going to... We had... Hang on. Wait. Here we go. This one, right? Our semi... Okay, so we could make this like x squared over 16 plus y squared over 12 equals 1, and then shift and make it, since we know where the foci are, right? That would end up with this. Which would also make x equals 2 plus 4 cosine t, and y equals 2 root 3 sine t. Right, but I shifted by the amount that our focus was. Again, at this point, the blarg. Anyway, we're doing polar integrals, so you really need to be able to take... It doesn't matter. I don't need it to be symmetric. So when you're taking integrals on polar equations, then we can use whatever equation we have. It doesn't matter what you've got. So this was 2 plus 4, and this was 2 square root 3. So this still puts a focus at 0, 0. And we'll do big mode. All right. Right, so we could do a few different things. So one is that we could actually use that shift to get us the polar version of all this other stuff in trying to do like trig substitution. It'd be pretty gross. But actually, I don't think it is that bad. But anyway, in polar form, right, we end up with x equals 2 plus 4 cosine t, y equals 2 root 3 sine t. Yeah. Right, but it's a quarter of the amount of time. So I thought that was the whole point. I'm okay with that. Or is the problem that this one in particular is going to get us that it's not going to account for actual time? This is going to just account for angle. That really, this is not t, this is theta. Okay. Yeah, we did something like that earlier. Alright, ads are coming up in 2 minutes, so let me know if there's anything else that we're gonna look at. If anybody does have any questions, anybody new, anybody who has a question directly related to GRE, awesome. If you don't, that's perfectly fine. You can always just ask whatever other kind of question you feel like. So I do tend to specialize in differential equations and precalculus and calculus. So if anybody is interested in that sort of stuff, please ask. I also do some other, I teach, or I used to teach, everything from basic algebra all the way up through differential equations. So anywhere in that whole stretch, I'm pretty good with, generally speaking. Statistics can... It was okay. I got through it. That's the other thing about statistics is, honestly, it's just a completely different vibe. And we still need it. Okay. Yep, so I'll see you all in 3 minutes. I'll just hit it now. So thanks everybody for coming in, and thanks everybody for sticking around. We'll come back in 3 minutes with hyperbolas. Hyperbole is the best thing ever.
bright, it's hard to breathe, but that's alright.
Another one. Well, unfortunately, this does mean I'm going to do fewer this time. But hey, thank you, Seth, for keeping us fit tonight.
Kids screaming in their cradles, profanities. Some days I feel skinnier than all the other days. Sometimes I can't tell if my
Yep, okay. Try not to bonk myself in the head. There we go. Oof. Yeah, call it good for now. Okay. Oh. Cool. I bought a new plastic thingy for my chair to roll on. It's awful. Like my old one had the little spiky things that go into the floor, so it would keep it in the same place. This one does not have that, so it just keeps like bunching up. Every time I roll on it, it just keeps making big wavy bits in it. I should have drawn those in first. That's alright. Yep, other way. Alright, so what we're looking at here is that we have this difference between the two terms, and more importantly, the two foci that we get no. So if we do the same sort of convention that we had last time, F1, F2, lowercase, being the focal distances to whatever point we're on the actual hyperbola itself, x comma y. F2 minus F1, absolute value, technically, if you want to worry about, like, you know, which branch you're on, is going to be equal to a constant. So in this case, we're looking at the distance between that's fine. Alright, it's the difference of the focal distances to all points x, y will be constant. Right, if the y term's negative, then we end up getting a horizontal hyperbola. So whichever one is positive is the direction in which it moves, asterisk, as long as your 1 is the thing that's positive on the opposite side. right? The bottom or topmost points are going to be our vertices, as always. It looks an awful lot like a parabola, but these are actually asymptotic to those things. If your y term is negative, yeah. Oh, gotcha. Thank you. I mean, I also want to come up with the equation for this for, like, by using the difference definition as well, but yeah, I don't think I have it. And yeah, this particular property is a little wild too, right? Where if we that's totally right there. Oh, getting their equation in there. So one example was foci are at plus or minus 3, 0. And the difference as above is 2. find that hyperbola's equation. Yeah, I guess. No, actually. So this is, the point of this one is that this is a new, like, request, right? That this is coming through and saying, well, let's find the actual equation of this particular hyperbola. So yeah, this one is going to end up being horizontal. As the difference of two distance formulas. Yeah, pretty much. That's not where I wanted to. It's here. So yeah, we're looking for here F1, F2. This is going to be F2 minus F1 is going to be equal to 2. So the difference between F1 and F2 is going to get us 2, and that is true for all points on the hyperbola, no matter where we are. Right, so F1 and F2 are the focal lengths. Yeah. Starting from the foci and then working toward any point we want on the entire hyperbola, but start with the easy ones, right? So if that is going to be 2 going between them, again, this distance from the focus to 0 on both sides is 3. Our right, if we were to draw in the rectangle thing, then we know that the vertex has to be at A and negative A. Because normally, right? If we're just looking at the standard one, x squared, yeah, x squared over a squared minus y squared over b squared is 1. X squared minus y squared equals 1 is going to yield us, right? A and b are both 1. If our y values are 0, then x is going to be either plus or minus 1. So yeah. And that'd be true if we make b literally anything. Right? As long as b squared is a positive number, we end up with the same properties. So we're going to get x equals negative a and x equals positive a over here. So, oh, hey, what do you know? F2 plus F1 is equal to 6. Right, that's just the distance straight across between the two foci. And then the difference between F2 and F1 at any particular point. So again, in this case, let's pick either of the ones that are along the x-axis. We end up getting that F2 minus F1 is 2 and, or when, F2 plus F1 is 6. So this means that if we were to clean these up, right, this implies that F2 is the bigger one, but without loss of generality, we could trade places with them. So this is 2F2 is equal to 8, so F2 is equal to 4. And F1 is 2. Just wanted to plug it into both. Okay. So if F1 is 2, that means that our hyperbola is going to have those a values at plus and minus 1. Right, so it goes from 0 to negative 3, for example, on the negative side. But then F1 is a distance of 2 away from our focus point. So distance at 2 away gets us onto the hyperbola at x equals negative 1. So that means A equals 1. And then we got to figure out what B is. I feel like we shouldn't just pick a random point. Seems hard. Okay, so if we go like this, and we choose a point, oops. Such that this is B. What do we know? Okay, so like this is 1 comma B. And we also know that the foci have a difference. In this case, f1 minus f2 is going to still be 2. And again, I think the best way to do this one is to cut this here, make a right triangle, and again, make those the hypotenuses. This one's 3. This is at an x value of 1. And this one's a height of B. What's up? Find the center. 0, 0. I already found A is 1. That's up here. I'm looking for B. Oh, middle point here. Yeah. No. That doesn't work because it has to be on the hyperbola. Center to a focus is 3, right? Right, but in that particular case, if you're going along the x-axis, then y is equal to 0, so it eliminates the b term. But where's your point x comma y? So that relationship's great and all, but it's not getting us a point that is on the hyperbola. Like, I guess it's doing a distance of some kind, but I'm not. Maybe it's just me being tired. I'm just not seeing it. Right, which at the moment is x squared over a is 1 minus y squared over b squared is equal to 1. I guess if you're talking about this one, that triangle there, right? This would be a comma b. This would be a comma 0, and that would be 0, 0. Is that what you meant? That'd be A, that'd be B, and it's the diagonal of the rectangle that we're using, which also happens to be C. I don't know why that has to be or why that has to be true, but that is a given property. So, like this triangle here, it says this is C, but like, I guess why? Apart from it told me. Alright, this is going to be A, this is going to be B. Which we don't know what B is. We're told C is, well, we're told this is C. I don't know why that's C necessarily. Apart from, again, we're just told that it's true. That's a whole lot of inline text. Yeah, can always do it, Famish. We've already had some pretty good ones already, just looking at conic sections here. Alright. Hmm. Right, this is XY. That's not B, that's Y.
When your deodorant has been reduced to a tiny whisper and tries to tell you, I'm running on empty.
Okay. F2.
Your new deodorant is already on its way, arriving today with Pride.
Absolute value.
Essentials delivered fast. Cut-off times and T's and C's apply. See product.
In this particular case, it's just going to be F1 minus F2. Switch it around. Going to assume. Since we're going to be in first quadrant. Alright, F1 is going to be the square root of parentheses C plus X squared plus Y squared. Minus square root. F2 is parentheses C minus X squared plus Y squared. So yeah, this is going to end up, yeah, with the same formula, essentially. Nice. Well, good luck, Famished. we'll be hanging around anyway. We are currently butting up on 3 hours. I think that's probably going to be pretty close to where we're going to leave it. As soon as I get the alert for the ads coming up, I think we'll probably go seek out Dr. Gold or any of our other friends who might be doing math streaming tonight. I mean, from me. I'm sure there's plenty of people. Oh, that's a minus. That's also a minus there. Okay. Alright, c squared plus 2xc equals 4 plus 4 square root. Get rid of that extra straight dot there. Nobody needs that in their life. C minus x parentheses squared plus y squared plus c squared minus 2xc plus x squared. Ooh, where'd that go? Okay, x squared and c squared are gone. That's going to stack up and make a 4 cx. Fours on the other side as well. So cx minus 1 is equal to the square root of parentheses c minus x squared. No, c minus x squared plus y squared. Alright, c squared x squared minus 2cx plus 1 is equal to, multiply up, c squared minus 2cx plus x squared plus y squared. Alright, 2cx is gone. What were we even doing? I wanted to find other stuff in terms of C. We wanted to find oh. C squared x squared minus c squared plus 1 gross is going to be equal to x squared plus y squared. Alright, so I'm not getting x squared plus y squared equals c squared at the moment, but that's also not a and b, so Larg. Alright, we'll figure this out later. For right now, let's go find somebody. In the next 2 minutes, Dr. Gold's up. Yep, been 27 minutes, so he's got plenty of time left on his. We'll start heading on over there. I will be back on Wednesday, certainly, for more mathy type stuff. And then we'll do more gamey type stuff on Friday. And maybe some other days we'll just decide what we're going to do. I'm going to be spending some more time in Elite Dangerous and cleaning up, finishing probably the Tasher Sector settlement that we're doing now. And maybe picking up another one before then, so who knows. Anyway, I'll see you all hopefully Wednesday for more mathy stuff, or Friday for more gamey stuff. My name's Obi-Wan Pez. This is N Simplex Pachinko. See you later.